But first I'm going to do what will unquestionably be the best part of this project and remove the covering off this plate. Yep, alright, we're done here. That's all I really wanted to do. Hello Internet, my name is Quinn and this is Blondihacks. Today I'm going to make this contraption. This is for holding a dial test indicator concentrically with your mill spindle for dialing in parts. It's useful in all kinds of setups and you can make one yourself. So let's go. Here's the DTI holder that I've designed, and this is sort of a simplified version of the articulated arm type that you can buy commercially. My design is literally and figuratively less flexible, but is within the reach, I think, of a hobbyist to make. So let's give it a go. As always, these models and drawings are available on my Patreon if you'd like to make one of these guys yourself. Here's the material I have for it. It's actually aluminum gauge plate. It's intended for fixture making and such. It was a donation to the channel. It's excessively fancy for this project. And then I've got some aluminum round bar and some brass that we'll need as well. This stock is precision ground on both sides, and from these big gentle arcs here you can see it was probably done on a Blanchard grinder, which is those big turntable grinders that you might have seen. It's a very efficient way to grind a lot of things or very large things all at once. Very cool. I'm going to lay out the clamp feature first for the spindle. I think this part is a great candidate for layout here. There's really only one critical dimension, and that's the ID of the spindle clamping area. Everything else is just cosmetic, so layout will be a good way to, make the part look about the way I want it to. I've got the main ring laid out there, and then I'll measure the distance to the small bore, punch that, and then that's going to be the hole where the little riser goes that holds the slider, as you saw in the CAD drawing. And that's it. That is the part. Pretty simple to draw, but it's going to be quite tricky to make, as we'll see here. I'm going to start by rough cutting this out on the bandsaw here. I need a smaller chunk to work with here. And while I'm at it, I'm also going to cut a long chunk out for the slider bar, which will be made from this same stock. I didn't do layout for the slider bar. That's a very trivial part that I can just make with the DRO alone. I'm going to start here on the lathe with the large center bore. That's the critical feature here. Now the trick is to get this thing parallel to the face of the chuck. So I'll start with some parallels behind it there to get me in the ballpark. I need clearance behind the part for the boring bar so I don't hit the chuck jaws there. So that gets me close, and then I'm going to dial in the face here with the indicator. So I just find the high spots and tap those in. When I'm going to dial in a part and I need to set the face like this, I always find it easier to set the face first, because once it's sitting square to the jaws, it tends to stay that way. If you dial in the concentricity first and then try to straighten it, it's much harder. The face is running within 1/1000th there, so now I'm going to dial in the center, and the trick that I like for this is to put your dead center in there and stick the tailstock live center in the dead center, and then you can just dial in the dead center, and that dials in the punch mark there. It's theoretically possible for it to fall out while you're doing this, so I keep a board down there, but in general I find this works extremely well, and it's actually a very quick way to dial in a punch mark. Then a quick double check on the face again, and yeah, that's running out a couple of thousandths now, so it did move a little, but that's still good enough for what we need here. You can generally tell how well both of these worked just by spinning it up. Keep your eyes on the punch mark and the scribe lines, not the smudge marks. And you can see that the scribe lines and the punch mark are running very true there, so that worked very well. Now we're ready to make some chips. I'm going to start with drills. I'm not going to bother with the center drill here because we're going to end up at the boring bar, so it doesn't matter if the hole is on center. Any eccentricity in the hole is going to be taken out by the boring bar anyway, so this is just about speed. Get as much material out of the way here as we can for the boring bar, so I'm going as large as I can on drills, which, because this is aluminum, I can go pretty large. This is an 1.1/8" drill, which most of the time my lathe just cowers in fear at, but because it was aluminum, I kinda got away with this one. And then I finish up with the boring bar, of course. I measured my spindle before I started this, and it's 1.730 inches, so I'm aiming for 2 thou over that, which should be a nice, easy sliding fit. You don't want to go too much larger or the clamp action won't work very well, but too close and it'll be difficult to slide the clamp on there. So that should be it. I'll do a deburr here before my final dimension check. Telescoping bore gauge will reveal the truth here. Survey says 1.732. 3.1 and 9.9. I don't know. I'll take it. Quick test fit on the spindle here, and that is good. That's what I was hoping for. You can slide it on there pretty easily, but it's a very close fit, so the clamp doesn't have much work to do. That's kind of what you're looking for with a part like this. Next, I'm going to set it up to drill the small hole next to it that holds the little riser post. So for this, I'm just eyeballing it on the scribe lines there with the center drill. Nothing too precise required here. And then I'll drill that out in 2 stages, and I'm going to finish with the reamer. I'm reaming this because I want a slight interference fit on this riser post, so I want an accurate dimension on that hole. Now for the rest of this part, it's out with the vise and in with the rotary table. Yeah, we're going to do some interesting rotary table stuff here to finish out all those roundy outer details of this thing. You can't turn the OD of it on the lathe because of course there's that little ear in the way. So I'm going to bring in my corner rounding fixture here. There's a Morse taper there with a threaded center, and I'm going to line it up on the mill thusly. An offcut at that gauge plate will make a nice sacrificial parallel here for cutting this OD. And I'm figuring out which way to put it. I think I'm going to align it here with the 0 thusly on the rotary table. It's going to get clamped into the center eventually, and I'm using the other hole for a second clamping point, but temporarily I'm going to clamp it on the edges so that I can bring in my coaxial indicator and dial in the inner diameter there. I'd like the outer diameter of the part to be reasonably concentric. It's all cosmetic, so it doesn't have to be perfect, but you know, I'm trying to make it as good as I can here. So I'll tap that in until the coaxial indicator says it's running true. Now I don't need access to the center anymore, so I'm going to put in a center clamp here with a scrap of aluminum angle, and now I can remove the clamp that's on the outer edge there because I need access to the outer edge for milling the outside. Now I can translate over to the radius of the OD here, and I'll just do a dry run around the outside there. The edge of the end mill should follow my layout line there perfectly, which it looks like it does, so I think I'm in good shape. I'm going to start by plunging the fillets at each end where the 2 radii meet. I just eyeballed the location according to the layout lines, and I noted the angle on the rotary table so I can get back here later. I plunge that one, and then I do the same thing on the other side of the little ear there. That should give me nice matching fillets on either side there where the 2 curves meet. Those plunged holes then become the starting and ending points for the side milling. You can plunge mill a lot more than you can side mill, so plunging the holes to start with prevents chatter when the end mill gets into the full side contact that would occur at the end of the cut at each end here. Now I could probably do this side milling in one pass, but I didn't trust my clamping arrangement here a whole lot. That piece of aluminum there in the middle is a little flimsy for a clamp, so I took light cuts and did a couple of passes there, and that seemed to work really well. Now I'm going to use my end rounding fixture as intended. I'm going to put in one of the little center buttons there that matches the radius that I have on the small hole there. Clamp it down, and then a jury-rigged something on the back side to clamp the other side down. Once again, those starting plunges that I did form the starting point for this radius cut. I find that starting spot by feel, and then just crank the rotary table around again until I get to the other side. This is a much better clamp, so you can see that I just did this cut in one pass here at full depth. There's the basic form of this clamp now. It's looking pretty decent. I didn't do a perfect job of blending those curves together there where they meet at the fillet there, but I can blend those together with a little bit of filing here. I deburred everything, and then some treatment with a needle file there blends everything together, and that is looking much better. Once again, it's all cosmetic. Just try to make it look as good as I can. If those fillets and radii were critical, you could do a whole bunch of math to make them perfect on the rotary table, but that just isn't necessary here. Onto the slider bar now. Here's that rectangular chunk I cut out of that gauge plate. And for this, I just need to square up the edges to start with and bring them down to dimension. The nice thing about this gauge plate is that the opposite faces are, of course, extremely parallel, so I can just clamp them straight in the vise like this, mill all the edges, deburr it. Now I've got 4 of those sides nice and square. I'm also going to clean up one end because it's going to be the reference for the features here in the center. The other end doesn't matter, it's going to get milled away later. And I'll find the center line because that's going to be the reference for everything, and then find the end so I can translate down and put in 3 holes. I'm center drilling both ends of the slot, and then I'm also center drilling and pilot drilling out the end where the dial indicator is going to clamp in. This hole gets reamed to a specific dimension because conveniently the mounting bosses on DTIs are a standard size, so we can match that size very closely here, once again so the clamp doesn't have much work to do. Now I can mill out the slot. I usually start with a light cut here just to make sure everything's okay, and then I'll finish it up with 1 or 2 more passes. The ends there are pre-drilled because that allows me to plunge at each end without the end mill having to do any work in the center. You can, of course, plunge with a center cutting end mill, such as this 2-flute, but it's nicer if you don't have to. The main challenge with slot cutting like this is always keeping the slot clear. You don't want to be recutting those old chips, so I use air and lots of cutting fluid and other means to make sure that that slot stays clear ahead of the cutter. A little deburring and cleanup, and I'm ready to round the ends of this thing. So of course for that, it's back to my corner and end rounding fixture. If you're interested in this fixture, I did do a video on how to make this thing. So I've got it set up there, and I want to get it aligned with the 0 angle mark on my rotary table. I use a square referenced off the other T-slot for that. And then I can bolt that down. And a simple 180 degree end rounding like this is very, very easy, much simpler than what I was doing earlier. For this, you just translate over the radius of the cut plus the radius of the end mill, and then run it around from 0 to 180 degrees. Could not be simpler. This is really the job for which I designed this fixture. Lately I've been torturing it into doing other things, but that is its raison d'etre. For the other end, I swap in a smaller pin to my fixture here. I have a selection of these pins for all different sized reference holes. And in this case I'm referencing the radius at the end of the slot, which also works just fine. Once again, aligning this with the 0 on the rotary table, clamp it down, and away we go. There's no center bolt on this particular pin because the smaller diameters don't have room for it. But if the part is small enough to have such a small reference hole, then you probably don't need 2 bolts holding it down. Over to the lathe now to make the riser, and I'm using the 4-jaw here for a very important technical reason, which is that it was on the lathe and I didn't feel like changing it. So of course I'll face the end, center drill, and tail support for that, and turn this down to the OD of the part. This is by far the simplest part on this whole job. Just very basic lathe work here. There's a small boss at one end that slides in that slider track thing that we just made. It has a threaded hole in the end that holds a clamping thumb screw. Then at the other end, there's a larger boss that is an interference fit in the clamp there, making those 2 pieces into 1 piece. I wanted to do this all in one setup because it was quicker, and so I used the grooving tool for this end. I just plunged into a dimension a little bit oversized, and then for my finishing cut, I plunged down to final dimension and then pan across, making a nice even surface. It's an easy way to get a shoulder on the far end of a part in one setup like this. And that works great if you don't blow the dimension like I just did. I checked it again to see if it got bigger, and no, it didn't. So as I was saying, that fit there is intended to be a Loctite fit in the clamp there. As stated clearly on the drawing here, that was of course intended to be a Loctite fit all along, which is why I made it a Loctite fit. And now I can go ahead and drill and tap the end there for the thumb screw. everything going perfectly to plan here on this component. To part that off to length, I can find the inside shoulder there just by feel on the parting blade. It's a nice thing about having an inside shoulder. Then I moved over the correct amount with an indicator on the carriage there and part it off. Pause and break that corner there, finish the parting. And Yahtzee. Out with the aluminum and in with the brass. I've got 3 little thumb screws to make, and I'm going to make them all in one long setup here. My collet chuck does not have an opening in the back through which you can pass stock, so I'm going to make them all with the stock sticking out like this. I'll show you some techniques for doing this if you find yourself in a similar situation. I turned the OD down to the largest diameter of all the thumb screws. And if you're wondering why that stock is currently a barbell shape, it's because I noticed that I was turning a taper, so I took this opportunity to adjust the alignment of my tailstock. I had plenty of material to remove here, so I paused, used the brass as a tailstock alignment bar, and resumed making parts out of it. The first thumb screw has a very small thread at the end, so I need to turn this down very close to the smallest diameter I can hold with this tailstock. So you can see me leaving a little bit of a stub there at the end. A little bit of material there around the cone of the tailstock there. I don't want to get the cutter into it there and damage anything. I'll cut that little stub off later. Then a shoulder gets turned above that slides in the clearance around the clamping feature. This will all make sense when you see how these parts go together. And finally I turn a knurl on the thumb part of the thumb screw, the action end of it. Look, I'm knurling things, okay? Look, you try narrating machining videos every single week. This is hard, okay? Go ahead. No, talk to my agent. No, I'll be at my trailer. I was, am, and perhaps always shall be a mediocre knurler, and this is no exception. That is, in fact, a mediocre knurl. However, here's a little trick that makes any knurl look a whole lot better. Chamfer both sides of it. The material gets pushed over the sides there, and a classy chamfer will clean that right up. It is quite surprising how much better a chamfer on both sides makes any knurl look. Now I can't put the thread on the end because of the little cone extension there, so I'll have to do that later, as you'll see. And I can't part it off because it needs tail support because of how far I am from the chuck. Now you could use a steady rest here, but here's a simpler way to get around that. Just don't part all the way through because you don't want to part with the tailstock in place, and then finish that up with a hacksaw. And then we can clean up the end here later. Again, all these little tricks are just in case you need to work on stock a long way away from the chuck and don't want to set up the steady rest. And now you know why the board is there. Now I can face the detritus off the end there and repeat all of those steps to make the next thumb screw. Just work my way down the stock, getting closer and closer to the chuck. The next thumb screw is basically the same, except it's got a very long knurl on it, so I'm actually feeding with the knurler here, which is kind of fun and exciting when you have to do that. There we have a very long mediocre knurl. So of course I will chamfer the ends to make it look 58% better. The thread on this knob is a little bit larger, so I can in fact put the thread on it now because I didn't have to make the little cone at the end for the tailstock. But we're still a metric mile away from the chuck here, so I had to put the tailstock back in, part some of the way through, and then finish with the hacksaw once again. By the time I get to the third knob, I've worked my way back close enough to the chuck that I can part it off the usual way. The hacksaw marks are cleaned up with a file, and I bring all of the knobs to this point here. Now 2 of those have those little cones on the end, so to remove those I just use a jeweler's saw to chop the very end of it off there, right where the diameter starts to change. Now I can put it back in the lathe to cut the threads on the end of it nice and straight. The collet chuck does a nice job of holding onto that knurl there without damaging it. Because this is brass, I can just turn the thread there by hand very easily with no mechanical assistance. And there's our tiny little thumb screw. Now comes the hardest part, that's making the little clamping features. I start by centering up with the edge finder here. To get the x-axis, I pick an arbitrary point on the curve there and then move around to the other side without adjusting the z height of the quill or column, and I find the same position on the other side, and that's a valid center because it's a consistent chord across the circle. I don't have access to the center line of this ring here any other way. I start now by very carefully milling down a flat spot here with a 2-flute center cutting end mill, just plunging down there to the height specified on the drawing. And now with that little flat spot, I can very carefully center drill with a long center drill in there, and now I can drill the tapping drill size all the way down. This I'm doing by eye here. I set the depth ahead of time in front of the part here. I want to go as deep as I can without breaking through the arch on the other side there anywhere. And I zero the quill DRO there to get my depth, and then I drill that all the way down. Next is the trickiest but most critical part of this, which is to open up the top half of the hole to a clearance size. That forms a shelf there upon which the clamping screw clamps. However, you have to be very careful not to drill this too deep. This clearance hole needs to go just to the split line, or a little below is okay. And I've just made the biggest mistake on this project. I don't know it yet though, so stay tuned to see how this turns out. Meanwhile, I'm going to go ahead and tap the thread now in the bottom half of the clamping feature there. The tap actually passes through the clearance and into the remaining tap drill size left at the bottom. So from above, it doesn't look like anything happened, but we tapped the bottom half of that feature there. Quick test fit now with the thumb screw, which should thread down all the way in there, and that looks pretty good. There's no signs of any trouble yet. Cue ominous music. For the little tiny clamp that holds the DTI, the process is exactly the same. It's mill a flat spot, center drill, drill the tapping drill, drill a clearance drill halfway down, tap the bottom of the hole, test fit with the thumb screw. Bob's your uncle. Next, to create the slits that turn these into clamps, so I'm finding the top surface there with the slitting saw using a feeler gauge, just so the saw doesn't scratch up the part. It's just soft aluminum here. Zero the Z. Find the bottom, use the half function on the Z, then bring the saw up to 0, and away we go. The nice thing about using the half function is we don't have to compensate for the feeler gauge there. That's automatic since I use the same feeler gauge above and below, and we also don't care how thick the saw is. So that's that. Now for the ring, it's trickier because I don't have access to the top and bottom, so I need to find the top, again with the feeler, then measure how thick the saw is. Now I can translate down the radius of the part plus the feeler plus half the thickness of the saw, and that gives me the center line. And once again, cut that through. Okay, let's test these clamps to make sure they work. So the DTI goes in there, and then I tighten that little thumb screw, and it's tighter, but it's not tight. So that's not quite good enough. That's not too shocking. The material's pretty thick, so the clamp needs a little more flexibility in it. So using a small end mill, I just plunge a little keyhole feature at the back there. People will also cut the slot deeper and then drill a hole at the end so it doesn't crack, but this also works just fine. And that did the trick. That was just the little bit of extra flexibility that needed. So that grips tightly now. Now how about the spindle clamp? I'll slide that on there, tighten the thumb screw, and yeah, that is definitely not tight. So this guy's not working. So once again, I put a little relief cut at the back and tested it again. Still no go. Now, it took me quite a while to figure out why I couldn't get a clamping action out of this. And eventually I did figure it out. You can probably see from this angle what I did wrong. Remember this drilling operation? That right there is the wrong size drill. I grabbed the wrong drill out of the box and I drilled it over size. So the little shoulder that the clamping bolt is supposed to sit on isn't there. And I just didn't notice until I tried to use it. After some adult language, here's how I decided to fix this. I've got some tissue wrapped around a feeler gauge and I slide that into the slot. You'll see why in a moment. And then I turned this little aluminum dowel pin to be a very close sliding fit in that clearance that I drilled. And I put some Loctite on that and I pushed that guy down into the hole. The feeler gauge acts as a stop, so the pin stops right at the top of the slot, and then the tissue absorbs any Loctite that might seep down in there so I don't get Loctite in the slot. Then once that's set, I mill it down and re-drill the clearance hole to the correct depth, just like I was supposed to do the first time. And there's the repair right there. And now let's give this another test. So here's that thumb screw once again. I thread that in there, and now you can actually see, if you look at that slot, as I tighten the thumb screw, you can see the slot close up. So that is now working perfectly. It's working really, really well, in fact. Now, if you notice that the thumb screw seems to look different, you are not wrong. I actually had to make that thumb screw again. I was trying to figure out why it wouldn't clamp, and I made a bunch of modifications to it. I shortened the thread a bunch, and I moved the shoulder, and nothing seemed to fix it. So I'd thoroughly ruined that thumb screw and had to make it again. Now I can Loctite the riser post in there as well. Once again, as intended, that was always going to be a Loctite fit there. That is the final assembly. So let's give this thing a little test fit on the mill here. So it slides over the spindle like so, and then that tightens down with a couple of turns there. Very nice. Then you just adjust the length of the arm here with the slider and that other thumb screw to approximately where you need it. And then you put the DTI in there and clamp that down with the third thumb screw. So I'll give it a test here by dialing in this scrap of round bar here. The idea is you get the length in the ballpark there with the radius adjustment. You can circle it around the top of the part there until you're close to it. The goal here is you have to get the motion of the arm there within the range of the indicator, which is pretty small for these little DTIs. Once you're there, then you adjust the indicator to face normal to the surface, then set the arm if you need to, and then use the quill to bring that arm down onto the surface. And then if you do all of that right, as you rotate it, the needle remains within its range all the way around, and now you can dial the variance out of it. I usually start with doing the left and right because it's easy to see both sides of the part there. So you dial half the error out of one side, and once those two sides are aligned, then you can do the front and back. And of course, the front is easy, but the back requires an inspection mirror or your cell phone or some other way to see what's going on at the back. Usually once you've got the left and right adjusted, the front is very close because it's going to be the same number all the way around. So usually one or two iterations of side to side and front to back is all it takes. This is actually quite quick to do. So that's now within a couple of thousandths. I mean, this is unmachined round bar, so the outer surface of it isn't particularly good. Let's do a more interesting test though. Here's a machined part, so we'll be able to dial this in accurately. This is a cylinder head that's definitely not related to, or won't be related to, depending on when this video is published, another project on my channel. I need to clamp it in place to this aluminum as you see here, but now the OD is not available for the coaxial indicator, which I might normally use for this. And that little shoulder there is too short for the coaxial indicator to read on. So this is a perfect case for a DTI holder like this. I can use the DTI holder and indicate within the 340 degrees or so that I have access to with the clamp there, and I can dial it in thusly. The nice thing about the DTI is you don't need a full 360 to dial something in. So in no time at all, I've got this dialed in to less than half a thousandths of run out all the way around there. I'm very pleased with that. It's working extremely well. If you're interested in making one of these, I would definitely call it like an intermediate level home shop machinist project. It's not for beginners. There's some tricky operations in here, but it's definitely worth the challenge. If you want to do a simpler version of this, get rid of the clamp that goes on the spindle and just clamp that riser pin in the spindle itself in a collet. The reason for the offset clamp though is because it allows you to attach this to the spindle while you have an end mill or an edge finder or something in the spindle already. You don't have to upset some other part of your setup. You can just throw this guy on, indicate something in, and then continue machining or whatever. Well, I hope you enjoyed watching me make this thing. I'm going to get quite a bit of use out of it, as you'll see in upcoming projects. Thank you very much for watching. Thanks so much to my patrons who make all of this possible, and I will see you next time.